So welcome everyone. So today we're very happy to have Yiming here. He's going to kick off the Friday seminar series for this semester here. And he's going to tell us about his recent work with Yibu and Huan.
Okay, thanks a lot for inviting me. It's I'm very happy to have another opportunity to speak before my graduation. So today I will be talking about this recent paper with Yibu and Huan, which is titled Estimating Global Charge Violation Amplitudes from Wormholes. So let's see. So well-known statement in quantum gravity is that any global symmetry in the low energy effective field theory have two possibilities. One is that it is approximate, and the other is that it is gauged. And in this talk, I won't be considering, at least for the most part, I won't be considering the possibility that the symmetry is gauged. So it is approximate, then it's unambiguous to ask how approximate can the global symmetry be? Can we put some lower bound on the violation of the global symmetry? Now, in this talk, let me focus on the simplest case of a zero form symmetry. So the charged objects are just point particles. And I will also make another simplifying assumption in this talk, namely, I will assume that this global symmetry is exact in the semi-classical theory. Namely, if we just look at quantum field theory propagating on fixed background, there is no effect that violates the global symmetry. This is, of course, not a necessary assumption, and we also don't expect it to be true generally. But here we are just making this assumption to look for the worst case scenario because we want to single out the non-perturbative effect coming from quantum gravity that violates the global symmetry. Now, this statement that the global symmetry must be violated in quantum gravity has a very long history. And here I listed some of the argument in the literature. To my knowledge, it really dates back to the first paper by Hawking about black hole evaporation. And in the 80s, Coleman had a lot of. Yes.
Hawking did not interpret it to indicate that there's no global symmetry in quantum gravity. He assumed there was global symmetry and interpreted that to mean the quantum gravity.
Right. But I guess maybe in the modern interpretation, we can interpret this result in a different way.
Must be nice.
Anyway, so in the 80s, Coleman had several papers about wormhole effects violating global symmetry. And these arguments have been later refined and made more rigorous in different settings. Most notably, there was a nice paper by Tom and Naki in 2010, and there is some recent development by Harlow and Uguri. So I think since I suspect not everyone here has thought about this problem before, I think it would be worthwhile to just have a brief review of the well-known qualitative argument of why global symmetry must be violated. So the most well-known argument involves thinking about the process of black hole evaporation. And the idea is that imagine we start to form a black hole with particles that carry some global charge, and we form the black hole with a very large mass and also a very large total charge Q. So here, let me just assume that the symmetry is U1 just for convenience.
Formalism of it is not that
question.
So it's a little hard to, well, it is hard to check if the model isn't technical.
We can't hear you. No, I think.
Right. So
You need to mute.
we may consider charges, maybe it's integrable, maybe it's not quite integrable.
Yeah, does someone have
There's some integrable models to analyze it.
Or is it correct to say that you have uncountably infinite?
Please continue, Yiming. We try to mute him.
Okay, let me just continue here.
With no integrable models only uncountably many
We form a very, very large black hole. Its Hawking temperature is very low. So during the most part of its evaporation, since the Hawking temperature is very low, you won't be able to emit particles that, let's say, the particles that carry this global charge Q has mass m. Since the Hawking temperature is much smaller than the mass scale, it won't be able to radiate particles that carry the global charge. In other words, the Hawking radiation only contains light particles that don't carry the charge. Of course, when the black hole gets down to very small mass, its temperature increases. So at some point, its Hawking temperature will be much greater than the mass of the particle that carries the global charge. Then it can, in principle, start to emit these charged particles. But Hawking's calculation suggests that the radiation is really agnostic about the sign of charge. So the black hole will emit both positive charge and negative charge at the same time. In particular, this the total charge, namely the statistical fluctuation, will be incomparable to the initial charge Q that you form the black hole with. Now, the last step to really complete the argument, one has to say something about the final stage of the evaporation. Now, we only trust the semi-classical description of the black hole evaporation, presumably when the mass of the black hole eventually reaches the Planck scale. Now, suppose that the black hole in the end fully evaporates into relatively light particles. Since the mass of these light particles are very small, because now the black hole only has the mass that is the Planck scale, Planck mass. Since the mass of the black hole is already very small, it's impossible to account for the huge initial charge that you use to form the black hole. So in this scenario, charge is simply lost. Now, another possibility is that suppose the final core of the black hole becomes stable, then one runs into problems with remnants. And there are various arguments in the literature saying that this scenario is also impossible. For example, as was argued in this paper by Banks and Seibert, that these stable remnants that carry arbitrary large charge would violate the covariant entropy bound proposed by these authors here. Now, I just want to say that it seems to me there are several rooms for improvement in this particular argument. For example, this argument involves certain assumptions about the final stage of the radiation. But we would expect that such a generic phenomenon of global charge violation shouldn't really rely on these very delicate assumptions. And it also involves comparing the initial state and the final state of the black hole evaporation. So it's kind of unclear dynamically when the violation effect happens. And it's also very specific to the black hole background. There has been some recent development that gives certain refinement to this old statement. These new developments are based on ideas that are behind this new progress on the black hole information problem. And I think Henry gave a talk here in 2020 about a paper that we wrote together, which points out that you can really do a very concrete calculation, which shows that global symmetry is already violated. Already you can see the effect at the page time. So already this removes any assumption that you need to make about the final stage of the Hawking evaporation. And I think the interesting thing here is that the violation can really be quantified by computing a very explicit quantity, which is a particular entropic quantity of the Hawking radiation. So this Henry talked about in the seminar here in 2020, and there has also been some other papers discussing some recent refinements in this subject. Okay. Now, the main point of the talk today is rather to discuss the even simpler setup. Well, we don't rely on the black hole evaporation background, and we look at the simpler setup where we can say something concrete about the global symmetry violation. Before I jump into the detail, let me just say a few words about the reason that we might be interested in this question. So one motivation for me is to understand how exactly semi-classical gravity can constrain UV physics. So in recent years, we've seen the usefulness of semi-classical gravity methods in computing the page curve, etc. So I think it would be interesting to understand its application in some other contexts as well. Now, another motivation is that the no global symmetry conjecture is one of the most basic swampland criteria, and it's also closely tied to many others. So I think it would be worthwhile to understand it better and see what we can say about it. But for in this room, I think it would be interesting to mention that the most important motivation is really that Nima asked us about it. So I hope after the talk today, Nima can give us a grade for the answer that we get. Okay, so the specific setup that we consider, well, the natural quantity to consider is really a 2-to-2 scattering amplitude, while the initial state and the final state in the scattering amplitude carry different global charges. Now, this particular setup is a bit more difficult to study. And in our paper, we already considered an even simpler setup. The setup that we considered is in ADS. So we studied the problem that we scatter some spherical shells in ADS. Now, the setup is that we consider sending in a thin shell of matter carrying some global charge A and ask what is the exclusive amplitude that another thin shell of matter with a different global charge B that comes out to infinity. We studied this process mainly in ADS space because in ADS space it's easier to specify the boundary conditions. But I will say a little bit about flat space towards the end. Now, the reason we consider a spherical shell is because we can utilize the spherical symmetric to reduce this problem to a two-dimensional problem. So that makes the analysis simpler. And so here I'm drawing a picture of the ADS space. And after you dimensionally reduce to 2 dimensions, I will be drawing just a 2-dimensional problem where on one side you have the origin of the space-time at arc_0. On the other side, you have the asymptotic boundary. And you send in a shell A and ask what's the amplitude with the shell B that comes out. Okay. So before you send in the shell, we start with just empty ADS space. And after the shell B comes out, we're also left with only the empty ADS space. And something happens in the middle. So what we did is that we studied this problem in a general 2-dimensional dilatant gravity coupled to these thin shells. I will denote this amplitude as the amplitude of A going to B, and we're interested in studying the behavior of the dependence of this amplitude on the energy of the process. And our analysis will be only trustworthy when the energy is much greater than the Planck scale. We will consider the case where the rest mass of the shell is very, very small. So we're already scattering like highly boosted particles. In other words, the center of mass energy is much greater than the rest mass of the shell. And because of the assumption that I made at the beginning that the symmetry is exact in the semi-classical theory, if we just naively look at this calculation where we just have a single space-time and ask what's the amplitude, we will just conclude it's 0. In other words, to any orders in the perturbative expansion, the amplitude will just be 0. Of course, what we will be interested in is these non-perturbative small corrections to the amplitude that are not captured by just a simple semi-classical calculation. And one will also expect that these non-perturbative corrections might be highly fluctuating as you change the energy. It might be a highly fluctuating function in the energy. So, okay. So what's the strategy to compute this quantity? Now, we'll be following the idea behind many recent discussions of black hole information problem. The main idea is that we don't attempt to compute this quantity directly. Instead, we try to compute the square of this quantity. In other words, we try to compute the square of the amplitude with suitable average. So we take the mass square of the amplitude, and after you do some average, these fluctuations are washed out, and we're already computing the typical size of the amplitude. Now, there can be different ways to interpret the average here. I think most naturally, one can simply think of it as just averaging over some tiny high energy window. So let's say we average over some small energy window around some center energy E. In other words, as I said, we are computing the typical size of the amplitude. Now, here we are not necessarily requiring the theory to contain random couplings, but if it does, one can also interpret the average here as an ensemble average, as averaging over the underlying couplings of the theory. Okay. And the idea behind this recent development is that such averages are captured by wormholes. I think this is essentially Coleman's insight in the 80s, but I think it's further refined by these recent discussions and made the logics made more precise. Now, the idea is that one would look for an onshore wormhole solution that contributes to the swell. So the reason that one would have a wormhole here is that when we set up this problem, we will have one asymptotic boundary with A going in and B coming out corresponds to the amplitude. But since we are computing the swell, there is another asymptotic boundary which corresponds to the complex conjugate of the amplitude. Well, we have the A dagger, which is the conjugate of A operator that comes out at the other boundary, and the conjugate of the B operator comes in at the other boundary. Okay? And since you now have two asymptotic boundaries, if they are just disconnected, you will still have the conclusion that the amplitude swell is again 0. But now since you have two asymptotic boundaries, one can consider the possibility that they are connected by a wormhole in between. So schematically here, I'm drawing a cartoon. Well, there is a wormhole connecting these two ADS space. And the result of this wormhole is that this A particle can have the possibility of going through the wormhole and comes out at the second boundary. And similarly for the B particle. And that's the reason that even though here we are still even though here in an effective description, we are not breaking the symmetry explicitly, but the existence of the wormhole can lead to a non-zero result of the square of the amplitude. Okay. Now, I want to say that the conceptual work is already essentially done in the literature. What we already did is to do an honest calculation and try to understand the property of this geometry better. In other words, to turn this cartoon into a more concrete onshore solution. Now the solution turns out to have some exotic features which puzzled us quite a while. So I will be mostly focusing on discussing these features. To really discuss how we construct the solution, let me here just emphasize that the solution here has the basic structure that it has three parts. So it has the basic structure of going from a geometry with energy E prime to a geometry with energy E, and then transits into a geometry with E prime. And between each part, there is some spherical shell in between. Okay. So the strategy in constructing the solution will be, we will first look at the solution where we just have E prime going to E with one shell in between. And then after we understand that that solution better, we will try to patch the solution together and get in the end this wormhole geometry. Okay, so as I said, the step one of the construction is that we first look at the solution with just one shell, but have energy E and E prime on two sides of the shell. Just to make, so even though in the end, I would like to take E prime to be 0, but to help you understand the property of the solution better, here I would take E and E prime to be general and discuss the general situation. Now, this solution with only one shell and E and E prime on two sides can be also interpreted as computing such a quantity, which is we insert a projection operator with energy E prime, and then the operator A, and then a projection operator with energy E and the operator A dagger, and compute the trace. Now the saddle point geometry that contributes to this particular quantity is given by solving different parts of solving different Euclidean black hole geometries along the shell. Let me talk a little bit about how this works in the general two-dimensional dilaton gravity. So the action of a general two-dimensional dilaton gravity can be written as follows. So in our paper, we use the slightly less conventional notation for the dilaton. So usually people write the dilaton as phi, but in our paper, we use the notation S because the dilaton here already has the thermodynamic interpretation as the entropy. namely the extremum value of the dilaton will be the entropy of the solution. So we use the little s to denote the dilaton. And there could be a general potential T of S of the dilaton. And the gravity part of the action is coupled to the action of the shell, which we take to be some general function M of S times the proper length along the shell. Now, this is some effective mass because generally when we do dimensional reduction from high dimension, this mass function contains, for example, the volume of the sphere of the spherical shell. So it can depend on the dilaton in a more general way. Okay. And the general solutions of this action has the following form. So away from the shell, the solution would just be some Euclidean black hole metric. So here I'm drawing the Euclidean black hole. So this is the tau direction, namely the Euclidean time direction of the Euclidean black hole. And this is the radial direction, okay, which I label by rho. And you can have different parts of this geometry, which are Euclidean black holes with different mass, and they are glued together along the shell. And you can solve them by looking at the junction conditions along the shell, which are described by many people in the literature. Okay. And after you construct the solution, you can evaluate its classical action. And it turns out that the classical action of this general problem is has a very interesting form. So if you look at the classical action, the first piece, there is a piece that only comes from the fixed points in the geometry. Namely here, in each part of the geometry, there is an isometry that corresponds to translating the Euclidean time, tau. And if there is a horizon in the problem, then there is a fixed point of this isometry. If for each of these fixed points, there will be a contribution to the action that is the value of the dilaton at that point, which is the same as the entropy of that Euclidean black hole. So, for example, if we look at this geometry here, we will just have one fixed point which corresponds to the value of the dilaton here. And there is another piece to the contribution of the classical action, which comes entirely from the shell itself. So this is some integral along the trajectory of the shell. But in the limit that we're looking at, namely the shell is very, very light compared to the mass of the black hole or compared to the center of mass energy. This term is really very, very small. This term is much smaller compared to the leading term. So in the later part of the talk, I will be mainly focusing on the leading term, namely the entropy contribution to the action. Now let me then tell you what the general one shell solution looks like. Okay. So if you just have one shell, the result is that you will find that the shell always lies on the side with a larger energy. So imagine we are looking at a situation where the energy E is smaller than E prime, then the shell will be closer to the solution with greater energy would only cover a very small portion of the geometry. And most parts of the geometry will be covered by the solution with a smaller energy, okay? In other words, in the limit, where the rest mass of the shell becomes zero, the shell will be really very, very close to the boundary. And the geometry with greater energy only shows up very close to the boundary. Now, in the opposite situation, where the energy E is greater than E prime, we just have the opposite situation where the energy E prime covers the most part of the geometry. And in this case, if we just focus on the leading part of the action, we will just find that whichever energy is smaller, the action is given by the partition, the logarithm of the partition function is given by the minimum of the two entropies, namely the entropy of the black hole with the smaller energy. Now one can interpret this diagram, there's a way to interpret this particular diagram as computing the probability of a black hole which starts in energy E and then emits a huge radiation and becomes a black hole with a significantly different energy E prime. Okay? And such probability goes like e to the s of the smaller, of the entropy of the smaller black hole, the entropy of the black hole with energy E prime, divided by all the possible initial states that you can start with, namely the entropy of the initial black hole. And that gives that the probability goes like e to the minus delta s, which is essentially the difference in the entropy of the two black holes. So this particular factor has been discussed by some people in the literature. But here we see that it comes out from a very simple construction.
Weren't they doing this in flat space? This is Hawking radiation from or tunneling, right?
Yes.
This flat space? They weren't doing ADS, I thought.
Yes, in fact, the solution that they discuss is actually different from the solution that we found.
Okay.
But I think our solution is much simpler, and somehow it gives the same answer. I don't know what to say really about their solution.
Okay.
I think this is the simplest calculation that gives you the correct answer that you expect.
When you got the same answer as them?
Yeah, it's the same answer.
Okay.
So the difference, well, let me highlight a particular aspect of this of this calculation. So in the Lorentzian signature, if we cut this geometry open and continue into Lorentzian signature, this particle really comes out from the past horizon of the black hole with energy E. But in the actual calculation that we are doing in the Euclidean signature, the shell is really always very, very close to the boundary of the space-time, and it never really comes close to the horizon. I think this highlights a particular aspect of the calculation that we're doing is that we're already considering situations where the black hole is in thermal equilibrium with its environment. So it really doesn't matter whether we're extracting the particle from the near horizon region or we're just extracting it from the far away thermal atmosphere of the black hole. Okay. So I think in their situation, their calculation might be suited for the case where the black hole is not in thermal equilibrium with its environment, let's say in flat space that is 0 temperature far away. Then there is no choice but to extract the particle from the near horizon region. And that might involve a more complicated solution. In our solution, since in our situation, we are looking at the thermal equilibrium, so it really doesn't matter where you extract the particle. Now, once you understood the one-shell solution, you can start to construct the solution that we actually are interested in, namely a solution that has a transition between from energy E prime to energy E and then to energy E prime again. Okay. So to construct this, we can start with a solution that we already have and use the so-called cut and glue procedure to get the final solution. Now, let me just first tell you how it works if we are interested in the situation where energy E is smaller than energy E prime. That is not the final situation we are interested in because in the end, we want to take the energy E prime, namely the original energy to be 0. But this case is simpler to understand. So we have this one-shell solution. We can simply cut the geometry open at the other end, at the other side of the Euclidean disk, and patch it with another part of the identical part of the E prime geometry, joined along with the shell that is corresponds to the B particle. Okay. So in this case, starting from a one-shell solution is pretty easy to get a two-shell solution with A dagger and B dagger on different sides. And the action of this particular solution will simply goes like e to the s of E, well, E is corresponds to the energy of the black hole in the middle. Of course, the action also involves small corrections that are negligible when the rest mass of the shell is very small. But now, what's puzzling is that in the situation that we're actually interested in, namely the energy E is greater than E prime, the shell is already on this side, and the black hole with energy E only covers a tiny part of the geometry. So it seems that different from this situation here, we have no place to cut because this is already very small. There's no place to cut and join it to another part, another geometry with energy E prime. So does that simply mean that the solution doesn't exist? So this is a puzzle that puzzled us for a very long time. But it turns out that there is a formal analytic continuation of the solution in this regime, namely E is smaller than E prime. One can start with this solution and ask about what happens when you slowly decrease E prime, and what does the solution turn into? Okay. So there is a particular quantity that you can look at in the geometry that helps you to understand it, which is the Euclidean time separation between the particle A and B. So in this picture that I draw here, the particle A and B are separated by some large and positive Euclidean time. But once you start to do this analytic continuation, namely taking E prime to be small, you see that when energy E is greater than energy E prime, we will actually find that this Euclidean time becomes negative. If we just naively accept this, then it will mean that geometrically, what the wormhole solution, well, what the solution look like is really we have a large portion of the E prime geometry and another copy that is associated with the shell B and the B dagger. And in the middle, it is connected by a black hole geometry with energy E, but well, we analytically continue the Euclidean time along the boundary to be negative. So in other words, the Euclidean time separation between this point and that point is negative. Now, if we simply look at the analytic continuation of the original solution that is well behaved and ask what is the action for this new exotic solution, we will find that its action actually goes like e to the 2 times the entropy of the with energy E prime minus the entropy with energy E, okay? So somehow this negative Euclidean evolution is closely tied to the minus sign that we get in front of the entropy factor.
That just comes from the dilaton gravity evaluating.
Yeah, that's just evaluating the on-shell action of the action that I wrote earlier. Now, if we further take the limit, well, E prime is equal to 0, we would simply get a geometry where we start with an empty ADS space on both sides. And in the middle, there is a black hole geometry, but with a negative Euclidean evolution. And since in this case, we don't have the entropy of with E prime anymore because E prime goes to 0, the final answer that we get would just be e to the minus s. Well, s is the entropy of the black hole associated with energy E plus some small corrections that are sublimiting. So at this step, we seem to find that the amplitude squared is exponentially suppressed by the entropy that goes like e to the minus s. Of course, this is a very natural answer one would expect, since if we just ask about the overlap between the black hole microstates formed by collapsing A and the black hole microstates formed by collapsing the spherical shell B, the typical overlap will go like e to the minus s over 2. So the square would simply goes as e to the minus s. But here we see how it comes out from an explicit calculation involving this exotic geometry. But of course, the main question one will ask here is that does it even make sense to consider this analytic continuation? But does it make sense to consider negative Euclidean evolution? So here, let me say some nice thing about it. First of all, it seems essential in this particular calculation to get the expected answer. In other words, it seems very crucial to have a minus sign here rather than a plus sign, which wouldn't make sense. Now, another point is that inserting, so here, since we have a negative Euclidean evolution, that means that if we look at it from the boundary theory, namely if the gravity theory is due to some quantum mechanical system, it means that we're inserting a factor of e to the beta h in the boundary theory. This is generally a very bad idea in the canonic ensemble because we will have to sum over infinite high energy states, which makes the answer diverge. But here we are fixing the energy, so perhaps it's not as bad as one would imagine. Now, another good thing about this is that one can actually verify in the case of JT gravity that what we get from the semi-classical geometry, semi-classical calculation matches with the exact answer, which people computed using the Schwarzian theory. So in this slide, I'm flashing the exact answer, which was worked out by Herman and collaborators. So in the case of JT gravity, there is an exact formula which is known that is given by some factors of the density of states of the black hole with energy E. So S prime here is the entropy of the black hole. So there are some density of state factors, and there are also some products of gamma function. So M here is the rest mass of the particle. Yes.
What is this the exact result for?
Right.
Sorry, this is the exact result of with a disk, and you have 4-point function, four operators on the disk. And you are looking at the situation, maybe let me try. This is the result of this amplitude with 4 operators inserted, and look at this channel of construction of the operators.
Insertion times have been Fourier transformed so that the.
Yes, so
Yeah.
usually people compute it by fixing the time separation between the operators. But here, since we are looking at a fixed energy basis, we are doing a Fourier transformation to fix the energy between in this part and this part.
And that transformation doesn't blow up with the e to the plus beta h when you, okay. There's no issue from the negative you put in h.
So the idea is that you have some expression in the expressed in terms of the time separation.
Yeah.
And then when you do the Fourier transformation, you can do for the saddle point of the time interval.
Mm-hmm.
And it turns out the saddle point for these time separation between these 2 points will actually be negative.
Okay.
Negative Euclidean amount. But we can compare the answers expressed in the energy basis. And here, if you expand the exact answer from JT gravity in the regime where the energy energy E is much greater than energy E prime, you get this this expression here. And here we just want to focus on the leading contribution, which comes from the entropy factors. And you do see this 2s prime minus s comes out from the calculation. One can also match the subleading corrections to the semi-classical calculation, and it also matches precisely. And another thing you could check is, as I just said to Matt, that you can explicitly check this time separation in JT gravity in this situation, and you do find this negative amount. Yes.
Does negative time separation correspond to looking at a different ordering of the operators on the boundary?
No, the ordering is, I think here we are supposed to think of it as analytic continuation. So the ordering is still the same, but it's just that the time separation becomes negative.
So before you make the Fourier transform to definite energy, because you have to integrate over all times to make the Fourier transform.
Yes, yes.
Can't I think of it as like crossing symmetry as for like usually we analytically continue amplitudes related to different channels, like crossing symmetry.
Yeah, I'm not sure what's the other log here.
Okay.
Okay. So in the case of JT gravity, we do see that it agrees with even though being very exotic, it does seem to agree with the exact answer. But we do think that there is nonetheless some problems with this negative Euclidean evolution. One thing that is obvious is that it is really hard to reconcile with the conventional Lorentzian picture of the scattering. We think that after you scatter the shell, it takes some Lorentzian time for the other shell to come out. what does it even mean that the time separation between the two shells is some Euclidean amount, not only to mention is negative. But another point is actually related is that when there is bulk interaction, which is absent in JT gravity, namely if you have bulk quantum field and there are some interaction vertex in the bulk, one would expect that the fluctuations are not suppressed. I think it's fair to say that we don't really fully understand how to really study quantum corrections on this negative part of the geometry directly. What we partly understand is that you can first do the calculation when there's positive Euclidean evolution and then do the analytic continuation. But there is some simple physical reason that you do expect that the fluctuations are not suppressed. For example, one physical process you can imagine is that before this shell A really goes to the center of the ADS and maybe form a black hole, when it's still far away, it might emit some particle chi that stays at some large radius. And then this chi later gets absorbed by this shell B, and then it comes out to infinity, before it comes out to the infinity. Now this process will be enhanced compared to the original solution for the simple reason that after the shell A emit this particle chi, it would have a lower energy, which I denoted by energy E tilde here. And since the final result is highly suppressed towards high energy, this process where you emitted the particle will be much greater than the process that you didn't emit the particle. If we look at this negative part of the geometry, it would just mean that, well, if we had some particle chi going from one shell to the other, and similarly for the other, there should be another particle on the other side, the energy E prime in the middle will be smaller, and it will give a much greater contribution to the final answer. But generally, we don't expect the fluctuations on this background to be well defined. But so we spent some time thinking about this, and it seems to us that there is a particular improvement on the construction that solves this problem. So it turns out that there is an important ingredient that has been left out in the discussion. The geometry, the orange part of the geometry in the middle that I drew earlier already has a zero mole classically. Namely, it has a zero mole where we can shift one of the shell, we can rotate one of the shell relative to the other. Okay? So the Euclidean geometry has this classical zero mode, which means that we are really free to insert some large amount of Lorentzian evolution on the top part of the geometry as well as the bottom part of the geometry. Okay? So I can cut this Euclidean disk open and insert a very large Lorentzian evolution here and there. I cut it open here as well. Now, this motivates us to consider a more sensible quantity, which is an amplitude. Well, we fix the energy, but we don't fix the energy precisely, but we fix in some small energy window. While at the same time, we fix the time to be some large Lorentzian time. Okay? More concretely, you can look at this 2-point function of A and B, and instead of just doing a Fourier transformation to fix the energy precisely, you multiply it by some Gaussian function, which roughly fix the time to be around some time t. So that would be some quantity that is associated with this diagram in which you inserted some very large Lorentzian time. Now, why would this be helpful? Now, let me first give you an intuitive reason of why we think this will solve the problem. Let's recall the example that I told you earlier that the shell A emitted a particle before it forms a black hole. Now, if we had a large Lorentzian time in between A and B, intuitively, the particle that is emitted by the shell A would fall back into the horizon after some time. Now, if we really want to consider this diagram, well, the particle stays at some large radius. the probability of it staying at a large distance is suppressed exponentially, controlled by the quasi-normal mode decay associated with this particular excitation. In other words, we expect this particular diagram to have an exponential decay dependence on the Lorentzian time t with some frequency, quasi-normal mode frequency, the imaginary part of the quasi-normal mode frequency. Another way of saying this is that if we cut the geometry open in the middle, only the Hartle-Hawking state is invariant under this boost evolution, which we inserted, namely this large Lorentzian evolution. Any disturbance coming from the initial state that we insert this particles A and A dagger would die off as you go to very large Lorentzian time. So what we propose is that there is an improvement on the construction where we insert a Lorentzian piece of the geometry into the solution. And we expect that the fluctuations are suppressed at long time. The one way to draw the geometry is that we cut this Euclidean disk open and join it to two slices of the Lorentzian two-sided black hole. And in the middle, you have this boost evolution, which takes you from one slide to the other. Okay. And let me also mention that such a construction is very similar in spirit to some construction by Schenker and Stanford in studying the spectral form factor. Now, another way to quantify this effect is that one can actually try to compute the distance between these two shells. So here, naively, since we have some negative Euclidean time, the distance would be negative if you do a naive analytic continuation. But if you, after you insert this Lorentzian time, you can actually see that the distance becomes large and positive, even though you have this negative Euclidean part in the geometry. This, I don't want to go into detail here, but you can roughly think of the distance between these two shells as given by the distance between these 2 points. And as you add, after you evolve in Lorentzian time, the distance between two sides of the thermal field double or the two sides of the two-sided black hole grows with time linearly. Okay, let me also make some comments on this construction. That one potential issue that you might worry about that is that there might be long-lived quasi-normal modes, such as modes that carry very large angular momentum. So in other words, you might worry about that this initial shell emits some particle that carries some large angular momentum, which spirals around the ADS space for a very, very long time. This was also recently discussed by Doverson and Gibriadov in some paper, where they computed the quasi-normal mode frequency of these particles with large angular momentum. And it was found that it would generally be suppressed by some power of the angular momentum. So, so if in such situation, since our original shell has some finite mass, it can't emit a particle with arbitrarily large angular momentum. So one would expect that by going to long enough time, one can suppress these modes as well. But one might need to wait for a time that is some power law in the mass of the shell. In other words, some power of the center of mass energy. Another comment is that the flat space limit of the solution naively seems quite straightforward, in the sense that the final answer that we get separates into a universal piece that is simply the entropy with the energy E, and another piece that is related to the insertion of the operators that really has to do with the trajectory of the shell near infinity. So from this point of view, one might think the difference of the flat space case and the ADS case would simply be some difference in the exact way how you set this problem up, namely how you already inserted these operators. But it won't affect this universal piece that is the entropy suppression. However, one would have hoped, and we have tried to see whether one can have a more straightforward flat space or just simply a Lorentzian construction without going to ADS space first? I don't think we have a very good answer to that point yet. A related problem, as I've also briefly mentioned earlier, is that we're already considering a situation where the black hole is already in a thermal equilibrium with the environment. One would expect a further suppression if in a real scattering process, if the temperature is much lower far away, because in that situation, the black hole will want to emit Hawking radiation. And since we are here, we are looking at the exclusive amplitude where the black hole doesn't emit any Hawking radiation, where we expect a further suppression at long time. Let me also mention that if the symmetry is gauged, then we will simply get zero, because in the case where the symmetry is gauged, the integral over the zero mode of the gauge field along the throat of the wormhole will simply forbid charge to flow through the wormhole.
Something I'm confused about here is, what if you had a discrete gauge symmetry with, like, you know, a Z million or something like that, where so that would be reflected in the presence or absence of some string, but where does that enter your calculation?
You mean in this gauge symmetry part?
Well, imagine there's no long range gauge field. It's a discrete gauge symmetry. So I don't know, you Higgs it was charged in some U1 that you Higgs down to
yes,
a Z a million, right?
Yes.
So that could definitely forbid the 2-to-2 scattering, the 3-to-3 scattering. We have the same issue in the standard model, right? The standard model, baryon and lepton number are anomalous, but the Z3 of B plus L could be exact. It could be a gauge symmetry. So any calculation for this, for the rate for QQ to QL, has got to know about whether there is or isn't a cosmic string or a string that detects that. But where does this wormhole calculation know about that?
So in this particular setup that I'm talking about, if you already have, even if you just have a discrete gauge symmetry, you will have to sum over the topological operators of the discrete symmetry, which will also forbid any discrete charge to flow through the wormhole. So in that case, even if you just have a discrete gauge symmetry, the amplitude will also just be zero.
But if you have a million, if the charge is a million, in this example, then it would be not zero.
Yeah.
So because that zero is only up to the Cn, so zero multiplied by n.
I see.
This shell is could be, I mean, anyway, this is a little point about whether the shell is to be thought of as zillions of quanta or a few quanta, I guess. But that.
Okay, so let me summarize. So in this talk, I discussed how to use the wormholes to estimate global symmetry violating amplitude at high energy. I think it would be very interesting to see whether similar ideas can be generalized to other contexts, in particular the weak gravity conjecture. I think there are several interesting proposals of how to use similar ideas to say something about weak gravity conjecture in the literature, but I don't think they are fully explored yet. So I think that would be an interesting direction to look into. And of course, it would also be great if one can make some convincing argument on the coefficients in front of the effective field theory operators. So here, since we are looking at a very high energy process where energy is much greater than Planck mass, and our wormhole is very fat and very large, it doesn't translate easily into any statement about effective field theory operators. But perhaps along some line of this dispersion relation, this kind of discussion, one might be able to say something. But I don't have further things to say about that. So that's all I have. Thank you very much. Yes.
The probability to define does not depend on the amount of self violation.
That's not
expected.
In some sense, you can think of it roughly as after the initial shell already forms into the black hole, all the information about the initial charge is erased. So the final answer already is insensitive to the difference of the charge between the initial state and the final state. That is only valid after we insert this very large Lorentzian evolution. So any memory about the initial state is erased. If we didn't do that, then you might expect some interaction between the initial shell and the final shell, which might depend on the difference. Yes, Vivo.
Yeah, for these quasi-normal modes of large J, so the real part grows as some power of J, or how does it?
So the real power will be basically the energy of the particle.
Yeah, and that's large. That's large.
Yeah, that's very large.
But that's what they interpreted as scars. And
I think this, when they say scar, they probably meant more like the imagined part is very small. So these are like leaf oscillation. If you look at 2-point function, that's
right. But they're also not like small excitations. They're highly excited.
I have a qualitative question. So, I mean, there is the global symmetry is there in the geometry, not being violated in Lagrangian and anything. So I'm trying to understand the interpretation. If I have some global symmetry G, then the state or the amplitude would have G. But if I look at the mod squared or the density matrix, then it kind of has G cross G with a separate G on the bra and the cat. And the averaging that you're doing is kind of reducing that to a common G that lets you intermingle the indices between the bra and the cat side, right? For example, if I had an SON, if I had n scalars with an SON symmetry, let's say I had, the scalar I and something else going in and scalar J and something else going out. The amplitude is, if it's SON invariant, it would have just some delta ij. So the mod squared would have some delta ij on this side and some delta I prime j prime on the cat side. And so it has two copies of G. It has an SON on the left and an SON on the right. And the averaging that you're doing is allowing some delta I prime I and delta j prime j, but it's reducing it to a common SON. Now, you might have thought that if the amplitude is really broken, I mean, the actual amplitude is not SON invariant. It has some funny things that transform under SONs or, just not SON invariant. So this is making an interesting sort of prediction, or I want to say either a prediction or it's a part of the answer that's being calculated, that when you average, whatever the averaging is over energy or whatever, that the result is again SON invariant.
Yes.
That's a little funny, right? I mean, if the amplitude is just breaks the symmetry, why would averaging restore the symmetry? So is that a prediction, or do you think there's a sort of part of the average, which is SON invariant, that's being captured by the calculation, and there's some other part which is not being captured by the calculation?
I think here, one thing you could maybe relate it to what you say is that you would expect the true amplitude would not be, of course, would not be zero, but in this approximation that we're doing is really given by some Gaussian variable like Rij, well, R is some Gaussian variable. So when you take multiple copies and do average, you do get the structure we are talking about. So that's, I think it's a particular prediction of this wormhole discussion is that.
Yeah, but it's a little unexpected that if the amplitude is breaking the symmetry, why after averaging over energy or whatever, physical averaging you would do, I mean, the amplitude is tiny, is exponentially small. So you'd think if you mod squared an average, you'll still get something exponentially small, but which sort of violates the symmetry. But you're saying that the wormhole picture tells you that no, after you average, you restore the symmetry again. Yeah, anyway, so I guess one possibility is that that's really true. Another one is that there's a part of the amplitude that restores the symmetry that's being calculated by the wormhole, and some other part which doesn't, which is not.
I think this point has also been proposed by other people that you can interpret global symmetry as really a symmetry of the ensemble of theories, not really a symmetry of the single member of the ensemble. But I agree it's not a priori seems to be necessary or has to be true.
And just a comment, I mean, this is a trivial comment, but the kind of spirit of this is like as anti-weak gravity conjecture as you could be, because somehow this says that you can restore, I mean, at least philosophically, because the sort of idea of the weak gravity conjecture was, well, if you have a global symmetry is bad, if you gauge it with gauge coupling 10 to the minus 7,000, it shouldn't be good all of a sudden, right? Whereas you're saying 10 to the minus 7,000, it's fine. Global symmetry is restored, but 0, it's not, and it's broken, right? So
Exactly,
it's,
yeah. This definitely
so-
bugs me a lot. Yeah.
no, I mean, but maybe it's true. I mean, maybe that's why it's a conjecture. But I'm just saying the spirit is really opposite.
Yeah, it seems in the literature, when people talk about these one-line conjectures, usually the weak gravity conjecture is kind of very, very close with no global symmetry. But in this point of view, they seem like really different.
Absolutely, yeah, yeah.
Not continuously connected. It's a point that also puzzles me.
With the reduction to like a JT gravity calculation, makes sense if the weak gravity conjecture was wrong. Because JT gravity, you typically are balancing, you know, the gravity part of the metric with some electric field or some rotation. So I don't know, maybe.
I don't understand. I don't understand why JT has to be. Well, what I say.
Well, to get a 2D JT-like theory, you need the black hole to be close to extremal, right? Was that an assumption that went into this, or?
Yes, but I don't see why that implies weak gravity conjecture.
Well, okay, I see it as, yeah, somewhat related, right? You don't want a super extremal black hole.
Yeah, the JT part is not essential in this discussion. It's just a particular setup. We can check the answer.
A very small tech question. When you said e to the minus s, you meant s with coefficient 1. So actually,
Yeah,
e to the minus s.
yeah.
That's a little cool. Was that obvious ahead of time that it had to be? I mean, by dimensions, it's obvious it had to go like s. But was it obvious ahead of time that it had to be literally s?
Not obvious to me. And we thought about a lot of different possibility of doing this calculation. Finally, it seemed like this is the simplest one, but it's the most universal one. It's just really the Dyson gravity, just the leading contribution is just the entropy. There are, of course, as you probably know, that there are these proposals of some complex trajectory of the shell, some tunneling problem. I think those might not be really relevant here. They might be interesting for some other questions. It would seem more non-trivial to get e to the minus s from those formalism.
Question. Well, let's thank him again.